part, atomic diffusion in ionic solid materials. Instead of talking more about in metals with different um, diffusion mechanism in different crystal structures, this part will put more efforts or focus on the ionic solid materials. And as you expected that ionic solid materials, so you will have cation and ion, which are positive charge, the ions with positive charge and negative charge. So what's the facility for cation and ion? And and the diffusion mechanism in ionic solid materials, we just focus on vacancy mechanism. Actually, it's similar with this one. And we are going to use the results directly from this part will be XV dVF. And we will and next, due to vacancy-mediated diffusion mechanism in ionic solid materials, so we will introduce two different vacancy formation mechanism. The first one will be the Ch4 defect, and the second one will be Frankel defect. And after this one, we will also introduce what's the extrinsic and non-stoichiometry effect. And here you can have a detail on page 177 in your textbook. And you also can compare this part, vacancy mediated diffusion part, with the um, page 22 in lecture 2. This part actually just we directly connect this ionic solid materials to battery, and the driving force will be the electrical field or electrical potential gradient. So you can compare this with this one because both this case can drive atomic or ionic diffusion in ionic solid materials. So let's move to ionic solid materials. The most important part in ionic solid materials would be the diffusion species are generally electrical charge. And due to here, the electrical neutrality must be maintained. The electrical neutrality is quite important here. And before we move to real ionic solid materials with positive charge and also the negative charge one, we need to introduce the Kroger-Wink notation, which means that how we name each ions. The A here can be the atom or the vacancy. If you're talking about the atom potassium, you put a K here. And also on your upper right corner here would be the charge state. If this atom with positive charge, then we will use this small black ball to represent the positive charge. And if is a negative charge, we use a prong to represent as a negative charge. And if it's neutron, then we use X to represent the neutron. And on your lower right corner would be the site. Where is this atom or where is this vacancy? For example, like here we talking about we have a vacancy here, so we use a V, and at the upper right corner will be a chloride. So the vacancy at chloride side and with one positive charge. Because actually chloride carry negative charge, right? But this chloride ion was removed. So now in order to maintain the electrical neutrality, then this vacancy will have one positive charge. And the potassium, there was a potassium ion here, but now potassium ion was removed from here. So left a vacancy at potassium side. And the potassium was one positive charge, but now will be this vacancy will be have or one negative charge to reach the electrical neutrality. So this is how use this notation you can well describe which each atoms and also the vacancy. Then let's move back. There are two like vacancy formation mechanism in ionic solid materials. The first one we call the Ch4 defect. Ch4 defect actually is you have a pair of cation and anion vacancies, a pair. Okay, so which means that the potassium ion and the chloride ion were both removed away and left a pair of vacancy. This we call a Ch4 defect. And the second one will be we call a Frankel defect. Okay, so here is just there's no Ch4 defect, and then we move to right hand side. You visualize that a pair of ion moves to the surface of less ions and left a pair of vacancy. This we call a Ch4 defect formation. Okay. And just for your reference, there's a small ball with positive charge. So we have a small size, smaller than chloride ion, because with this chloride ion with free electrons surrounded by chloride. Oh, chloride. So we have a larger size to represent this chloride or anion. And Frankel defect here, we use the silver bromide as an example. Silver with positive charge is smaller size compared to bromide. And what's a Frankel defect? Actually, also a pair, but it's due to one of the ion can be a silver or bromide moves to self-interstitial side. So you can visualize a pair of vacancy, left vacancy, and corresponding ions. So you can see the silver was here at the self-interstitial side, and left is corresponding vacancy, and also you have one negative, one positive, also reach the electrical neutrality. So it will be a pair of cation, self-interstitial, and corresponding vacancy. So it will be here. It also can be the anion, self-interstitial, and corresponding vacancy. In this case, it will be anion will be the negative charge, so it will be the bromide moved to the self-interstitial side and left a vacancy of bromide. That will be the other case. 所以从这里的话，我们就知道说，因为我们要讨论的是，离子材料它在 vacancy mediated 的情况之下，它的阴阳离子的 diffusivity，所以就要先讲说它是 vacancy mediated，所以它就需要先知道说，在这个离子材料里面有哪几个生成 vacancy 的方式。那生成是怎样的 vacancy？ 在 Ch4 的话，它基本上是生成，因为钾跟氯离子一对离子离开了，像这个离开到表面，那它就生成了一对的 vacancy。那这种叫 Ch4 defect。那 Frankel 的话，就是 either 是银离子离开，那里有一个银的 vacancy。那银离子离开去哪呢？它去 self-interstitial side。那这个就是之前学过的 interstitial mechanism，因为它可能去 split dumbbell 或者是哪一种，就是 self-interstitial defect，就前面提的那几种都有可能。像是我们前面在这里提到的这几种，都是 self-interstitial defect，就是刚刚讲的 Frankel， 可以吗 ？OK， 然后另外一个是在离子材料里面要记得 ，you always need to maintain the electrical neutrality， 好不好？然后另外一个是 notation， 这里只有小小的一个提醒是正的是1点，然后负的是1撇，没有问题。neutral 的话 不是真的不带电，它只是跟它原来比，像谁？像哦，sorry，这个颜色不太好，我换个颜色。像这有点太粗，是不是？等一下啊，嗯，好，OK，夹好了，potassium。像我要描述这个好了，我就会写 potassium，因为现在 potassium ion now at potassium side，那它跟它原来的状态比，它就是 neutron。所以如果我要讲的是这个好了，这个那它是 chloride 嘛，就一样 chloride now at chloride side，那它是 neutron。所以它的 neutron 事实上是跟它原始的 state 比，要考虑 surrounding 的状况。OK，那一样这个的话，这个是 bromide 嘛，所以这个一样是 bromide at bromide side and will be neutral，是一样的，可以吗？好，这个大家 for you read。OK， so next, because the case is potassium chloride or silver bromide, actually they are FCC. So I just grab the figures represent the FCC for sodium chloride. Chloride will be the anion. So showing green, so will be typical FCC here. You have 8 at the corner and 6 at the face center. And the red one, small one, um, is a sodium cation. So also will be the FCC. So take a look here will be the typical FCC structure as well. Okay, so it's FCC, double FCC structures for all these ionic materials. So in order to, the purpose here would be we want to know in potassium chloride, what's the diffusivity for potassium ion and chloride ions as well. So through what? Through Schottky defect. So this is a quick remind. When we use through the vacancy-mediated self-diffusion in ionic solid materials, you can grab the relationship you derive from prior section, XV which means that when you have a higher vacancy fractions, the diffusivity will be higher. So now it turns out if I want to know the decay, the diffusivity for potassium ion, I need to know the VK, the fraction of vacancy at potassium side. Okay, and the same idea for diffusivity of chloride. So I need to know the V, the fraction of vacancy at chloride side. So that will be the less important. And especially the based on prior knowledge, we know the fraction of vacancy will be related with vacancy formation gives free energy. So here, which energy control the vacancy formation will be Schottky defect formation gives free energy. So will be something linked with this. So in order to describe, there are Schottky defect form in this potassium chloride ionic crystal. You can write this equations or this one. What this means is before potassium at potassium side neutron, chloride at chloride side neutron. But move to your right-hand side, they generate a pair of Schottky defect. Vacancy at the potassium side with one negative charge, and vacancy at the chloride side with one positive charge, and the rest of them potassium at the potassium side, chloride at chloride side. So this can be this move to right-hand side represent there are Schottky defect formed in these ionic materials. Or you can rewrite and show like this. This will be the simplified equation, chemical equation. Now we don't have any Schottky defect, and we generate a pair of Schottky defect. Based on this equation, some people will write down like the K equilibrium rate constant under equilibrium condition will be this. fraction times this fraction, and this move to right-hand side equals to Schottky defect formation gives free energy divided by kT. So would be written like this. It's similar. So here, so how to get from here to here? So in order to persuade you, I write down some notes here. But just a quick reminder: this VK and VCL actually is a fraction. It's the same with V. This is a fraction. Okay, vacancy side fraction. Okay, even though I'm not writing down as a V because it's quite difficult to write down XVK, XVCL. So you, in your textbook, they use this to represent the vacancy size fraction. Okay, so now don't forget our purpose is we need to know the dk, right? So x this vk will be quite important, and VCL also important to get this one. Then I can know the DCL, right? So in order to persuade you this equation is correct, so I just write down A converted to C and D, and also reverse. So the forward rate constant is K1 and reverse is K2. So based on these chemical equations, you can write down the under equilibrium condition rate constant equals to K1 divided by K2. And also we know under equilibrium condition, K1 times this equals to K2 times this and this. So K1 is K0, K10, and exponential energy barrier, negative E1. And K2 will be back, right? K2 will be back, so energy barrier will be E2. And following here, I know K1, so the bottom will be A and the upper will be C and D. And K1 divided by K2, I can move A to a right-hand side. And also K1, you know this one, and K2 this one. So I can use this to divide it by this one. So I got a K0 and this divided by this one, this minus this one. So I got E1 minus E2, E1 minus E2, and this will be the energy barrier to generate CND. So this will be the gives this energy will be the gives this will be the Schottky defect formation gives free energy. Okay, so the same with this one. But at this moment, some people probably will argue why you have a K0 here, but no carry zero here. In your textbook, they actually ignore, or probably like put the K0 back to K equilibrium here. So you did not see this constant, but be honest, based on the series deviation, we should have a K0 here. Okay, so some people also rewritten like this, just have a long for both sides to get this one, but this will be more important. So don't forget, I just copy this one. In order to get the potassium and the facility for chloride. So I need to know what's this and this. But as you know, they are Schottky defect, right? They have a same numbers of potassium, vacancy at the potassium side, vacancy at the chloride side. So I got this equals to this. So I can write it down square because this is square, so I can get a VK will be square root over this one. So I got 2. So VK equals to this, right? So this is how this equals to this, I got this one. Okay, so now I already know the VK, right? So based on the equation you use in prior you derive from prior section. So dk, the facility of potassium, can be written as xvk, xv, dvf, copy it same. And because this is iron, so I will put a G is actually is a geometric factor, 就是不同的几何，晶体结构不同。G is ranging from 1 to 2. Now, here we use FCC. Sometimes if you change the different crystal structure, it will be different.
Okay, and the facility for chloride is the same idea. Because iron, I put G and X VCl, the passivity F. And here, don't forget, um, this is XVK, right? But the facility potassium here is this small black ball. If it want to diffuse, will be depending on the vacancy, the fraction of vacancy at potassium side. And it also make a jump, right? So it's a potassium jump in vacancy at the potassium side here. And for chloride, the same, the chloride here. So need to the fraction of vacancy at chloride side were determine the DCl, and also this chloride jump into vacancy at chloride side. So basically, as long as you write this down, you just fill out each term. For example, like XVK. XVK is VK here is this one. So I separate them in enthalpy and entropy term. And the other is the facility potassium at potassium. So uh I got the migration enthalpy. Migration gives energy, so separate them in enthalpy and entropy term. So it will be identical with this one. And also FCC, so I copy FA square mu, FA square mu here. So this will be the facility of potassium jump into vacancy at the potassium side, and the G here. And the same idea for chloride. So you already write this down, just fill each one. So this is vacancy at the chloride side. The fraction, so it will be involve the Ch4-2 defect formation, gives free energy, and separate them in enthalpy and entropy term. And the chloride is a migration, and migration is the same with I say BCC, so you have a square mu F and migration. And this migration actually AV is an ion jump in vacancy, cation in jump in vacancy, and we put a G here. So based on here, you know the diffusion activation energy for no matter it's a cation or anion will be the Ch4 defect formation enthalpy divided by 2 here, and the migration enthalpy depending on cation or anion jump in corresponding vacancy. So this is a Ch4 defect. So based on here, you know that you directly get the DK star and DCL star, and depending on Ch4 defect formation energy and migration term, right? And FCC, so you copy this result. If you forget the result, well, we can derive this one just here. Vacancy mediated one for FCC, so you got this result. FA square mu migration, vacancy formation. That this moment is a vacancy formation gives free energy and also migration one. So it's similar but slightly different. Okay. And next, I'm going to jump directly to Frankel defect. As we mentioned, the Frankel defect actually silver bromide. And based on experimental results or observation, you need to base on the experimental observation or literature. Which one, silver or bromide, is easier to move to the self-interstitial side? In most of cases, smallest one will be easier. So in this case, based on experimental observation, cation silver diffused by the interstitial C mechanism is dominant. So silver moves to self-interstitial defect and left a vacancy at the silver side. Under this situation, the same idea, I need to know the fraction of vacancy at silver side and the facility for silver. Usually a silver will be easy to jump into vacancy at the silver side F, right? But not only silver, I also want to know the bromide. So this will be a story. First thing I need to know the vacancy, the XV vacancy at the silver side. So based on the Franco defect, silver was at silver side with neutron, but generate the Franco defect, silver at the self-interstitial side with one positive charge and left a vacancy at silver side with one negative charge. This will be equals to this. So go to move to right-handed side, this will be Franco defect formation gives free energy, and this equals to this. So I can say that this equals to this equals to exponential negative Franco formation. Franco defect formation gives free energy divided by 2kT. This is equal. Okay, so I have a square, so take a square root of it. So I got this results. So the same idea for silver, I just put everything back. It because it's iron, and also this is FCC, so I put a G here. And silver actually moved to here is through interstitial C, so it'll be SIDIF. This is for silver. And for bromide, where is bromide? This big guy. Bromide, the only possibility to bromide to diffuse in this ionic material will be the vacancy, but here the vacancy will be silver vacancy. So it would be vacancy, and bromide jump in vacancy, but here vacancy will be at silver. Okay, so write it down and fill each one. For what's the fraction of the vacancy at the silver side will be Franco defect formation gives free energy divided by 2 and separate in enthalpy and entropy term. And the diffusivity will be, as I mentioned, a square F mu migration energy. This migration will be the silver migrate to self-interstitial side. And for bromide, the same idea. Vacancy is at silver side, the same. But the facility for bromide, this big guy jump in vacancy at silver side. I believe this migration energy is quite large. So this value should be quite small. Okay. It's quite difficult to allow bromide with negative charge and jump into the vacancy also with negative charge. It's like you have a repulsive force in between them, and also this big guy that will cause a large lattice distortion. So I believe this migration energy will be quite large. Exponential, you have a larger term that will be tell you that diffusivity will be quite small. So here the diffusivity should dominate by silver. So the diffusion activation energy included the Franco defect formation and also the migration energy, depending on which cation or anion we are talking about. Okay.